Now, we're going to completely switch gears back on you. We went to tensors because we were interested in our change of basis. That was our main goal. We're going to go back to the notation in the earlier chapter. So we're going to use our change of basis matrix C to look at the vector v prime and v. Same vector, different basis, with C causing the change in basis. So this is a change of basis, not a rotation of the vector. If it's an orthogonal change of basis, then we can say v prime, which equals C inverse v, actually equals C transpose v. And what we want to show is there are special cases where we can make a diagonal matrix out of the matrix A. So this is change of basis for A to D that is diagonal. So the question is a little more specific than just how do we change the basis. We saw when we looked at tensors that when we change basis for the vectors, the second rank tensors change basically by this M, A, M transpose generically. We want to look for a particular change of basis C that takes a specific transformation matrix A and turns it diagonal. Now, why do we like diagonal matrices? Why is this even something we want to do? Well, let's look at how a diagonal matrix behaves. Okay? We take our generic matrix M, and writing it this way assumes we've picked a basis, which we will assign to the column 1, 0. And there's lots of different notations we might use for it. E1 hat, E1 bra, the number 1 in the bra, in the ket, sorry. That's a 1. And we've picked 2. And we've assigned this to 0, 1. Now, if M happens to be diagonal, let's call that D, then it'll look like that. And the nice thing about the diagonal matrix is D on 1, 0 will be A times 1, 0. And D on 0, 1 will just be D times 0, 1. And the nice thing is, the first thing we notice is this diagonal matrix doesn't mix components. When I act on this basis vector, I get some factor times the basis vector back. When I act on this basis vector, I get some factor times the basis vector back. I don't get anything along the other direction. What do these two equations remind you of? Eigenvalue, I hope, right? This is the one thing I should have put in the pre-quiz. You've all seen eigenvalue equations, right? Everybody? Nod, yes. Lie to me if you haven't. So, this is the eigenvector equation. And the point is, it's obvious when the matrix is diagonal what the eigenvectors are. They're the basis vectors. And the eigenvector is exciting because the transformation does not rotate it. It only changes the length. And possibly multiplies by a minus sign. So it might flip it. Now, any matrix, whether it's diagonal or not, has eigenvectors. And the standard way to write this is like that. And the eigenvector equation is the central equation in quantum mechanics. If you understand this, you can do almost all of quantum mechanics. Now, physically, since I said this is something that does not change the direction of the vector, only its sign, imagine that A is the transformation that reflects about the line along 30 degrees above the x-axis. So here's my xy. Here's my line 30 degrees. What are the two eigenvectors of A?
The 30-degree line and the one that's perpendicular to it.
So the 30-degree line and the one perpendicular to it. Why?
Because if it's on the 30-degree line, reflecting about it is just going to keep it on that line.
Okay.
And the one perpendicular is just going to flip it by opposite side.
Okay. So now, with the person next to you, we've decided these are the two eigenvectors. What are the eigenvalues? Let's not shout it out. To the person next to you, what are the two eigenvalues? So we've claimed this is eigenvector 1. And here's eigenvector 2. What are the eigenvalues of those two eigenvectors? Find someone near you and decide on the eigenvalue. By the way, this should involve no algebra. This is a purely geometric question. Anyone want to give me an idea? 1 and -1. Because that's what the vectors become, right? You absolutely have to forget about the mechanics. You have learned eigenvalues and eigenvectors, and you spent a lot of time doing mechanics and solving equations. At your core, this has to be a physical intuition. And this equation tells me I take the vector and I map it to itself with some multiplicative factor. I just told reflection about 30, E1 goes to itself. The multiplicative factor is 1. So the eigenvalue is 1. E2 gets flipped to minus E2. So the multiplicative factor lambda is -1. You want to have that understanding. Now, let me ask you this. We also have, so that was reflection, if you recall. We write the reflection matrix that way. Let's suppose I rotate by 30 degrees. Now talk to the person next to you. What's the eigenvectors? So I'm going to rotate by 30 degrees. Talk about this one. What is the eigenvectors? What are the eigenvectors? Sorry, what is the eigenvectors? What are the eigenvectors in this case? Anyone want to take a guess at an eigenvector?
Has to be something on the complex.
Yeah. Is there any vector in the real plane here that has not changed?
No.
No. So it actually turns out, if you compute it, this is why we sometimes get complex eigenvectors. And so it's harder to picture. That's why I started with reflection. Reflection, the two vectors were real. The eigenvalues were real. It's easy to picture what you mean by that. Intuitively, a lot of what you will be doing are more abstract matrices, where the vectors that aren't affected are a little harder to picture at times, but you still want to know what they are. Now, if I was doing this as a 3D matrix, if I had a 3D matrix that was rotation in the xy plane by 30 degrees, now you know one of your eigenvectors. What's one of the eigenvectors if I'm in 3D?
Anything on the z-axis.
The z-axis, right? Because rotating the xy plane, the z-axis stays the same. So that there's going to be one real eigenvector. So there are times where it's a mixture. Some are real and some are complex. And we're going to see that one of the differences, if you look at these, if you were to describe these matrices, what's the difference between this one and this one in terms of words we use to describe matrices? And words we use things like orthogonal, symmetric, Hermitian, antisymmetric.
Asymmetric.
This is symmetric. This one is not. Right? This one, the sine and the sine thetas along the diagonal match. Okay? So we'll see later that that comes into it. But you really want to keep this picture in mind. It's very, very helpful. Any quick questions on the geometric interpretation?
So, what is an eigenvector, like, geometrically?
Geometrically, it's the vector that doesn't have anything changed except its magnitude, or it can flip. And so look at the reflection. The only any vector along here, under reflection, doesn't change. So that's an eigenvector.
Oh, okay. So you would specify a condition, and we think about what wouldn't change under that condition.
Exactly.
Or could flip under that.
Yeah, it can change by a minus sign.